Hello. Let's continue our exploration of causal analysis using R. Today's topic is interrupted time series. So here's a brief overview of ITS. ITS is a quasi-experimental method used to evaluate the impact of intervention by analyzing an outcome measured over time before and after the intervention occurs. So the data structure for ITS is time series, the long string of measurement over time. And the technique works by modeling changes in both the level and slope of the time series that follow the intervention, estimating both immediate and long-term effects. ITS is valuable when randomization is not feasible and can provide strong evidence for causal inference, but requires multiple data points on both sides of the intervention. And key assumptions include that the pre-intervention trend would have continued in the absence of the intervention, and that no major confounding events coincide with the intervention period. ITS is frequently used in public health, policy, and social science to assess population-level changes resulting from intervention or policy changes. So I just want to say we can perform causal analysis on different types of data. For example, James Robbins' G-estimation on longitudinal data with time-varying covariates. So the interrupted time series analysis is specifically for time series data. And in R, we have a package called its.analysis, which contains a very nice implementation of ITS. Let me show you. Okay, the library is its.analysis. We install it, load it in, and we can create synthetic data. So I'll create a year from 2001 to 2018. Okay, and then we have a hypothetical dependent variable. Just make things up. Have these continuous values in each year, and then we have another time series called the interruption. Okay, so assume 0 is the interruption is off, 1 is the interruption is on. Okay, so you can see it's off for a couple of years, and then it turned on for a couple of years and turned off again. Okay, so let's create that intervention, and we create a covariate, another potential confounder. Then we create the data frame, put everything together, and this is what it looks like. The year, that's the index for time, dependent variable, interruption, and covariate 1. So to run interrupted time series, we use the function itsa.model. And the syntax is data equal to x, time equal to year, dependent variable equal to dv, depth v, interrupt underscore var equal to double quotes interruption. And alpha, now we specify the significance level, the default is 0.05, and it uses bootstrap equal to true and reps equal to 250. So we're using 250 bootstrap samples, and we can run this code. And you can see it generates quite a bit output. Let's go back to the very beginning. So this is the call for that model's fitting statement we did. And first it provides ANOVA table and uses type 2 tests. So for some squares, there's type 1, type 2, type 3, type 4, sum of squares. Okay, so this is using type 2. So here you can see the ANOVA table. This is the bootstrapped F value, and also you can see from the ANOVA table, the dependent variable is significantly dependent on interrupt variable. So that's actually indicating a potential causal relationship between interrupt variable and the dependent variable. Because it's statistically significant, so it's significantly associated. But since we have off and on and off, so we're actually changing the interruptions, turn on, turn off, turn on, turn off. And every time we turn on and turn off, the outcome responds to that. So that's an additional strength for showing the potential causal relationship. And the lag, deep var, that is like a lag variable. So, and this is very significant. That means the current dependent variable value very, very significantly depend on the previous one. So this is just saying it's really a very popular feature of a time series. All right, and you have also the bootstrap f values and confidence intervals, and give you the result. It actually gives you a statement. So significant variation between time periods with chosen alpha less than 0.05. Okay, and then you have this model fit we just talked about, and then you have this two-key result. So it actually also does a two-keys test for multiple comparison of means with a 95% family-wise confidence interval. So here it's not really interesting because we only have two groups. So if you have three or more, then this will become more interesting. But if you look at the difference, the mean difference is group 1 minus group 0. So the intervention minus control, so it's a negative. That means when you switch from like you switch the interruption, it actually brings down the so you turn on the interruption, that brings down the outcome. It's declining. Okay, and some data and alpha level, and this its a dot result is the formal statement, a character string of the conclusion. You got the group means in more details, dependent variable, interruption variable. You got the residues. These residues are small, and fitted values. It did automatic. Okay. Okay. So fitted values. I don't know if you want to do residual plots or anything, but it does a few additional tests. Shapiro test is for testing normality of the data. Levin's test is to test the equivariance between groups. The out-core is the autocorrelation of the residuals. Okay, so this is not the outcomes, the residuals. So this is saying after we adjust for the lag dependent variable, then there's no autocorrelation. Okay. Which is good, and there's no post estimation warning, and adjusted square is 0.89. It's very high, indicating a good model. And there's also summary for the bootstrap, and also it gave us a plot on the right hand side. You can see the two vertical line, the dotted vertical line. That's where the interruption. So remember it was turned off and then turned on and then turned off again. So you can see when it's turned on, it brings down the outcome, and after a while it goes up again, and then you turn the interruption off, it goes further up. Okay, so that's kind of the output from that its.model fit. We can do a few variations. So we can do with covariate, different alpha level. So you can hear this syntax, everything's the same except you say covariance equal to double quote cov1 and alpha equal to 0.1. Okay, so you're still doing, you're still doing bootstrap. Okay, so again, it gives you similar output, but also you can turn bootstrap off. So here you can use everything's the same as the previous one, except you say no plots equal true and bootstrap equal to false. So basically, if you have large sample size and the data is approximately normal, you can probably do a quicker computation by using linear regression models. But if for the data is not normally distributed and you have a limited sample size, then Bootstrap is preferred. So let's run this. And also, I think it's much faster than the Bootstrap one. Okay, I think this is a tutorial to you to see how we can use R to implement interrupted time series analysis. Thank you so much, and please like our video and subscribe to our learning channels. Feel free to ask questions, give advices, and share this video to other users who may be interested. Thank you.